when you see this little integral sign, like if I say the integral from 0 to 3 of f of x dx, this is telling us to find the area, right? It's not doing it. Right now, all we know is this says find the area under the graph, right? And doesn't really have, and everything I've given you so far doesn't really involve anything dealing with calculus, does it? Yeah, you got that little weird symbol, but basically you're finding the area, right? Well, we're going to do that. Actually, I need, oh shoot. So the way, okay. Like, this little symbol means integral, and you have from here to here, it says find area. The way I want you to think of this, and this is huge, is I want you to think of, when you're finding area, is you're accumulating area. It's not like if I find what's the integral from -5 to -3 of this, if I'm looking at this rectangle, okay, I've got 6 rectangle, I mean, it's got 6 blocks, and so that's a -6. The way I want you to think of it is we're accumulating area, and if the area is below the x-axis, it's negative. If it's above the x-axis, it's positive. And in a picture, here's how I want you to think about it. Can y'all see that? I'm trying to put sound effects with it, because I think math should have sound effects, right? And if I keep going, and you can look, all right, so this is going, so I get a -6. And then if I keep going again, right? Oh. Okay. And if you look, right, you can kind of see these numbers. I don't know, we'll see it again. But it was negative, 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 and then this positive started canceling out. And if you look at it from the picture, you say, well, of course, this is negative, this is positive, these numbers are going to cancel out. Again, let's do it again.
This program is so impressive.
Yeah. Okay, right. It pauses. Okay, and then, here we go. All right, and you can kind of see the numbers, and you think, okay, look, all right, so this was -6. Okay, these canceled each other out. Okay, I got a part of a circle, and I get a rectangle, right? So this 8, this positive 8 cancels out this -6, so we get a 2. And that's part of a circle, right? And we go, of course we can do the last one. And we're, this accumulation. And I like this. Can you think of it as that we're adding little bitty rectangles? Right? Can you see the little bitty rectangles we're adding? Right? That's a little idea that's going to be pretty helpful. Are we okay with that part? And if you go this way, things are normal. Things are below the x-axis are negative. Things that are above the x-axis are positive. If I go this way, things are backwards. Right? If I go, and so if I accumulate backwards here, let's reset. See how that makes a negative because we're going backwards. Notice how this is going from 9 to 7. So we're going backwards, and so we're accumulating our rectangles, and so things are backwards. Now, that's slightly different than what you were doing before. Like before, it was static. If I said, what's the integral from 9 to 7, you think, okay, what's this area? Okay, it's backwards, so it's going to be a -3. The slight change is I want you to think of it as we're accumulating area. Right? So, with that, now let's look at our paper. Provided I can click the right button, all right? And we're going to practice accumulating. So what we're going to do is we're going to accumulate our area, and we're going to start off with basic functions. And the most basic graph I could create is a line, right? Nice horizontal line. And so we're going to practice accumulating area under this line of y equals 2. So everybody ready? Fill in your chart, right? So we're going to start. I want the integral from 0 to 0, right? Okay. So we have this thing, let's say half of t, dt. Just treat that as an x, we'll worry about it later. And so if I go to 0, if I haven't gone anywhere, guess what the accumulated area is?
0.
Perfect. All right. Well, now let's accumulate the area to 1. So I'm now to, I've gone to 1. So what's our accumulated area? If it's at height 2 and we've accumulated up to 1, what's our height? 2. Perfect. All right, so now we're going to go to 2. We're going to accumulate area up to 2, and we're going to get
1.
4.
well, 4. Are we okay? 2 times 4? Okay. And let's see what happens if we go to 3. Get the idea that's going to give me a 6. That's going to give me a 6. Then we're accumulating area, and that's an 8, and then that's a 10. Everybody okay with we've accumulated area under our graph? Right. Right. Again, we're starting about as basic as we can get. Right. I can't get any. I don't know if I can get any easier than just a horizontal line. Right. So now let's look at the next one. Okay. We're gonna ramp up the difficulty just a little bit. When we ramp up our difficulty just a little bit, all right, we have a slightly more complicated function. Actually, really, not really. Right? There's not much going on here, right? You just have a triangle, right? But we're going to do the same thing. I want to accumulate area from 0 to 0. So if I haven't gone anywhere, what's my accumulated area? 0. All right, now we go to 1. So I'm going to accumulate area. Imagine like little rectangles add up to here. And so now I'm looking for that area. So, oh, and I do apologize. The worksheet, I like the questions. I don't like the distortion, right? Because it's really squished. Right. This is one on the horizontal, but one on the vertical is this tiny thing. So I realize it's distorted, but I'm just pointing it out. But are we okay that the area of this rectangle, or the area of this triangle, or the area under this graph is going to be 1/2?
Yeah.
Okay. So we get a 1/2. Okay, so now we're going to accumulate up to 2. So I keep adding up my rectangles, and so that's 2 times 2 divided by 2, which is 2. And then I go to 3. I keep accumulating area up to 3, so that's going to give me 3 times 3, which is 9/2. And when I finally get to 4, okay, I keep accumulating area, so what's 4 times 4 is 16/2, gives us 8. Are we okay with this sort of accumulation part? Right? Again, not much different than what we were talking about when we did area, right? Right? I mean, you can almost do it like it's static, okay, what's individual. But if you can visualize that you're just adding little bitty rectangles all the way up, that's going to help the explanation later a whole lot. All right, so, well, we need more complicated stuff. So let's see what happens with a complicated graph. All right? And here's our little chart, right? So we're going to go through our little chart, and I said, well, okay, we're still dealing with what's the integral from 0 to x. All right, this part's a little confusing, and I'm very tempted to, when I do this, to just put x's everywhere. But honestly, to be mathematically correct, I need to have a letter here, and if I have an x here, I can't use x here. Like, these are 2 different spots, and you have to use 2 different letters. But if it makes you feel better, just think, hey, that's a variable, right? This is the function, so this has got a graph, which is this mess. And this x tells us how far we're going. All right, so let's look. At 0, have we gone anywhere?
No.
Nope, so it's easy to figure out that's a 0. If I go to 1, I've accumulated some area. Okay? And so I've got to figure out that area that I've accumulated up to 1. And let's say that's a trapezoid, so I'm going to give average of the bases, which is 1 plus 3 divided by 2. Okay, that's going to give me times the height, which is 1. Are we okay that that's a 2? All right, now we're going to add up. We're going to go to 2. So I get to add some more stuff. So what's that, 3? So 2 plus 3 gives me 5. And then I get to add some more stuff, which is, what, 3/2? Like this area is 3/2?
Yeah.
Okay.
13.
So I get 13/2. And then, uh-oh. Now when we start accumulating, we're accumulating negatives, right? So if I accumulate negatives, I got to figure out this area. So that's 1, 2, 3, 4. Or is that 2? Okay, so that's going to give me, I think that's going to give me 9 over 2. You know, here, normally I'm a big fan of keeping things in fractions, but I actually think decimals are going to make our life a little bit easier here. So we'll make this 6.5, and then make that, what was that, 4.5? And then we have some more area, so we're gonna, let's add another 1.5. So if I subtract another 1.5, that's gonna give me a 3. And then when I get to 6, I'm gonna add some more stuff. And so when I look at that part, let's see, that's 1 times 1 divided by 2, so I get to add a half, so that's gonna give me 3.5. Am I doing this right?
Wait, how? I don't think 5.
Yeah, no, that's right. That's right.
Wait, I don't think
No, that's right.
5
That's right.
is.
3.75.
No, I think that's right.
Wait,
Wait,
no,
I
I
got
got,
think it's
yes.
four.
No,
Should be
isn't
2
the triangle on the bottom 2? Yeah.
I got 6 is.
Oh, this is 2?
Yeah.
Oh, the second one is 2. Oh, whoops.
Yeah, I got.
So I need to take, so,
I'm so confused.
I think it's.
Wait,
I
they're
think
both
5 is 2.5. Wait.
Yeah, and then 6 is.
5 is 2 point, okay.
Yeah.
This is 2.5.
Yeah.
Okay.
6 is 3.
No, 6
No,
is 3.
3.
6 is 3 because we added a half.
And
Right.
6.5. I got 3.25.
That's going to give us 3.25. Okay.
7
then
is
it's-
just 3 again.
And then at 7,
Oh,
we
wait.
take away a quarter, right?
Okay.
Exactly 3. 8 is just 2.
And so we're back to 3. And then at 8, we're going to subtract 1, so we're back to 2. Sorry about my geometry failing there, right? All right, are we okay with this accumulation part? All right. So, has everybody written that down? All right. Just curious, what is the maximum value of f? It's in your chart.
6.5.
Are we okay? 6.5 is the maximum value of f, right? When does that occur? At 3, right?
Wait, how is it max?
It's the biggest value.
It's the biggest value.
Well,
What is our f? Is the big F is
so it's not max is in like the highest on the y scale.
no. It's well. I didn't ask for the max of little f. I asked for the max of big F, right? And big F is the area under little f. And so right now, the only way we know how to find the max of big F is look at our area. And fortunately, we have this nice little table that we filled out, right? Right? And if I were to look at this graph, like if I were to graph what does big F look like, it starts out at 0, gets all the way up to 6.5, it starts going back down, right? And at 2.5, and at 2.5 it goes up a little bit, then it starts going back down. Can you see if you were plotting this, you'd have this little wave, right? Now, before we talk about this, because there's another chart that says that they're interested in f prime. Now I actually have to talk about what's called the fundamental theorem of calculus, right? So far I haven't really done any calculus. The only thing that looks kind of like calculus is this symbol. But basically all we've done is area, right? So today, and I'm going to preface this whole thing is this is not a full-on mathematical proof, right? The full-on mathematical proof is very precise. They make a big deal about this being a t, this being an x, and then they get into limit definition of weird stuff. So this is not an official proof. This is just an idea of the proof, of where something comes from, right? So you don't even need to write this down. What I would like you to do is look at the picture. And so what we're going to do is we're going to start with, I'm going to define, and I've got x's and t's, but for me, the way I always think about this is, I think of big F as the area under the graph of little f, which is what we were doing in the previous 3 examples, right? You had a little f that was a graph, various degrees of difficulty, various degrees of complexity, and we found the area under it. And when we found that area, that gave us what big F was. Everybody okay with that part? All right. So now let's look at a very generic picture. And here's my very generic picture. My generic picture is, okay, here's my graph, here's my grid, and I'm just going to call this guy F. This guy is little f. And I'm interested in that, that's big F, and big F is the area. I would like to know, what is F prime?
Of little f or big F?
The derivative of big F. Right? And this is where we get a little theoretical, right? Okay, everybody ready for this? All right, so hold on. Right? What does a derivative measure? Yes?
Slope.
Okay. Okay, what does slope measure?
Rate of change.
Rate of change. Is everybody okay with that? In general, a derivative measures how much something's changing, right? And for a lot of cases, you can just look at the slope of a line, but if you think of slope of a line, it's measuring how fast something changes, doesn't it? How steep it is, the bigger, whatever, all right? So when I take the derivative of f, of my area function, what I'm looking for is, how does the area change when x changes? Okay? Right? So if I look at this graph, what I'm interested in, and here's 0 and here's x, when x changes a little bit, do you see that the area, my area function changes a little bit as well? Do you see as x, that's that accumulation function? Remember I said we're adding rectangles? If x grows a little bit, do you see that this grows? Right? Now it's not quite a rectangle, right? Because the top is kind of wavy, isn't it? But if this little change in x is really, really small, do you see that this is basically a rectangle? If delta x gets really small, we can say, well, that's close enough to a rectangle. And actually, what I'm going for is it's infinitely small, but we'll get there. We'll talk about that later, right? And so what I'm interested in is the derivative of big F is whatever the area of that rectangle is, right? So an area of a rectangle, it's base times height, isn't it? Well, what's your base? Delta x, right? So our base is delta x. Now here's the tricky part. What's your height? How do you get the height? This is a bit of a hard part.
Isn't the area of little f?
I think you said it.
The max.
Well, not necessarily the max. I want to know how tall that line is. Isn't that the height of your function?
Yeah, the height of your function, so the y value that you get when you plug in.
Are we okay that this is the y value when you plug in? X? Isn't that the height of your function?
Yeah.
If I plug x into my function, I had like a little x here, so if I plug that in, so I could say that this is equal to f of x, where f of x is the height.
Well, would it be f of triangle x?
Well, no, delta x is just the change from here to here. I've got to get to that. Delta x is your change in x. I actually have to get there. Huh. Well, that's interesting. See, here's what I find interesting about this. All right? What I find interesting about all this is, why is this? Oh, that's why I was having trouble. Okay. Okay. Now, I'm going to do a little hand waving and notation. That delta x, I want that to get really, really small. And the way in calculus, or the way we change delta x to really, really small change in x, is we change it from delta x to a little dx. And so you look at it and you think, okay, All right, so the derivative of the area function is just the little function, right? Huh. Okay, so what's the significance of this? Well, believe it or not, this is the fundamental theorem of calculus. There's like the first and the second fundamental theorem. I think this is the first one. I'm not quite sure, but what it's telling us, well, let's look at these two equations. Are you okay with this? You see, if you look at these two equations, does it look like we took the derivative of both sides? Like if you look at the left, it looks like we took the derivative of the left. And if I take the derivative of the right, it almost looks like if I were to take the derivative of both sides, do you see how the derivative, it looks like the derivative canceled out the integral sign? Everybody see that? And I'm still working on it. What's the best way to explain this? I didn't do a great job second period, and I'm doing a slightly better, but still not great job this period. But this is the argument where the derivative cancels out the integral. And if the derivative cancels out the integral, what that means is this integral symbol means it's an antiderivative. And there's a whole lot of stuff that I did a whole lot of hand waving is to try to connect calculus to it. But actually what I'm talking about today, so the derivative cancels out the integral, yeah, that's nice. But what I'm talking about today is we're going to, or at least the problems we're going to finish today in class and what I'm going to give you for homework, deal with, okay, if capital F represents the area of this function and then f prime is equal to f of x, what do you think f double prime of x equals? If I take the derivative of both sides, what are we going to get? Say it.
F of x.
All right. So if I start off where big F is equal to the integral or the area under little f, and I did some hand waving proof thing that f prime is equal to the actual function, and then you take the derivative of both sides, well, it means big F double prime is equal to f prime of x, right? And here's what I'd like everybody to write down. Okay? This is the chart I want everybody to write down because we're going to use that basically for the rest of the day. Is I want you to write big F is equal to the integral of little f. I want you to write down f prime is equal to f, and I want you to write down f double prime is equal to f prime. And put a box around it. All right? Okay, this is your key. This is our key to solving all the problems that we're going to do today, okay? Or the remainder of the problems that we're going to do today. Not only that, this is your key to solve one free response question given every single year. Okay? There's one, I can look any year. This is your key to solving one free response question. And when you see it, and we're going to go over some of these next week, when you see it, you do this. And now I'm going to show you how to use it. All right? So now let's look back at what we had. So we're going to go back here. Okay. All right, so first, okay, I do apologize. Here's my picture, but the chart here. So here's the picture. It now says this next chart is what is f prime of x, big F prime. Right? And what's about to happen is you're going to get some questions. They're going to ask questions about big F. Right? But the only information they're giving you is the graph of little f. Let me say that again. Right? This is a very common thing the AP exam does. They give you the graph of little f, right? And they're going to ask questions about big F, right? Well, the problem is you don't know what big F looks like, right? And you never will, right? That's the bad news. The good news is you don't need to know what it looks like. What you need to know is your conversion. If they say, what is exactly big F? You say, well, that's the area. If they want to know what big F prime is, you say, well, that's just what F is. If you want to know what big F double prime is, well, then that's the slope of F. Does everybody see how I'm using my key? Now let's see how we use that. Okay, at the very basic level, we're just going to compute values. This says F prime, big F prime. Are we okay that big F prime is just F? So what is big F prime of 0?
Wait, does it say F prime or F?
It's F prime that this just, I know I've made it 2 per page, but this is F prime. So what is, are we okay if I'm using my key, right? My key is, I need a little more room.
Big F prime equals F, so we just look at the y values in that graph, right?
Yep. All right, since big F prime is just F, if I want to know what big F of 0 is, that's the exact same thing as F of 0. Are we okay that F of 0 is 1? Okay, what is big F prime of 1?
3.
3. What is big F prime of 2?
3.
3. What is big F prime of 3?
0.
0. What is big F prime of 4?
Negative 4.
All right. Is everybody getting the values? Right. Big F prime of 5, we're back at 0. Big F prime of 6, we're at 1. Big F prime of 6.5, we're back at 0. Big F prime of 7 is negative 1. And then we get a negative 1. Did everybody fill out your chart? Is everybody okay? All right? And so we were able to fill that chart with this element of our key, right? It says, what's big F prime? And you say, well, I don't know what big F prime is, but I know big F prime is the same thing as F. And I can find anything I want about F, right? Is everybody okay with that part? And now is where it gets interesting, okay? So I'm interested in looking at parts C, D, and F. What happened to E?
And G.
Oh.
You went from F to G.
They have trouble with the alphabet, all right? They've got good questions, but their knowledge of the alphabet is questionable. That's about okay, all right? Okay, oh. No? Okay. So I'm just going to read the questions, right? So to read the questions, it says, okay, where is this increasing? Where is it decreasing? Where does it achieve a maximum and minimum? Find concavity and points of inflection. What does that remind you of? If they talk about increasing, decreasing, concave up, concave down, points of inflection, when did we do stuff like that?
Curve sketching.
Curve sketching. All right? Remember that we did that? Those are terms we did in curve sketching. And what was the one thing that the AP, the College Board, is not going to grade that I told you you need to do anytime you do curve sketching?
Points of inflection.
No. There's one thing, if anytime you do curve sketching, you do it even though it's not going to be graded.
The number line.
The chart, right? The number line chart. Y'all remember that? So what we're going to do, I mean, do you remember that's how we had to deal with them? Anytime you want to know if something's increasing, decreasing, concave up, concave down, even though they're not going to grade a chart, you draw a chart because it makes your life easier, right? And this thing is saying, okay, where is it increasing, where is it decreasing, concave up, concave down, points of inflection. This is telling me, draw a chart, right? Does everybody see that? Now, here's my problem. So one problem is I only have this much space and I need twice this much space because I don't need enough room for the question and enough room to work, right? So what I'm going to do is minimize this, right? And then basically what I'm going to have to do is I'm going to have to write this down, and you have to write it down, then I'm going to have to erase it, right? So that we can look back at the picture, all right? So I want to do a big F prime chart. All right? Because this is big F prime, that's how I can figure out if something's increasing or decreasing, right? Now, the problem is, did they give me the graph of big F?
No.
What'd they give me?
Little f.
They gave me the graph of little f. What's my conversion? If I want to know what's going on with, what is big F prime equal to?
F.
F. Does everybody see that?
Yeah.
See our handy dandy conversion?
Yeah.
All right? And so if I'm making this chart, hopefully I can, okay, there it is. Okay, so, well, if I'm making this chart, big F prime, I can look at F. When you're doing your first derivative test, what do you find first? If you're trying to find out where stuff's increasing and decreasing, what's the first thing you have to find?
Slope.
Sort of.
Points are, it's at 0, right?
Where's your derivative 0, right? Everybody critical points? Does everybody remember that?
Yeah.
Okay. Where are my critical points? Your critical points are where big F prime equals 0. Well, I don't know a thing about big F prime. Do I know where F is 0? Where is F 0?
4, 6, and
3.
no, 4, 6, and 7,
3,
5.
6.5.
Do y'all see these are the places where it's 0?
Yeah, that's 3 and 5. Right?
6.5.
That's 4, 6, and 7.
4, 6, no, I think that's 3, 5, and 6.5.
Yeah. Yeah.
Look back at your chart.
Yeah.
Yeah.
Right?
3, 5, and 6.5.
Okay, so 3, 5, and 6.5. All right, now to finish our chart, I need to know, is big F prime positive or negative? Meaning, is F positive or negative? What is F here? What's my derivative? What's the derivative of big F here?
Negative.
Positive.
Also, all
It's positive.
Right, so
Because remember, we don't know what big F is, right? We don't know what big F prime is. What we're given is little f. And so if I'm asking where F prime is positive, right? That's the same thing as where is little f positive. And is everybody okay that little f is positive from here to here? And so it's positive from here to here, so it's positive here, it's positive here. And so I know I'm increasing, and I'm increasing, and then I'm decreasing, and I'm decreasing. Does everybody see that?
The concavity is just when you change the signs, right?
Well, concavity is dealing with second derivative. We haven't done second
What
derivative.
is it when you like when the signs change?
That's dealing with second derivative. Let me get there. We're still working on first derivative. All right, based on this picture, where do we have a maximum? Based on my chart, where do we have a maximum? At 3 and 6.5, right? Just curious. Do you remember the one of those first questions? What was your maximum value? What was the maximum value? Look at that first chart we had.
It was at 3.
It was at 3. Do you see that? Also, look at that first chart. Does it look like there's a local maximum at 6.5? If you look at the y values,
Yeah.
right? Do you see how this first derivative chart is describing what f is doing? All right, next part. Well, I need to talk about concavity. And if I'm going to talk about concavity, that's the second derivative, big F double prime. I don't know what big F double prime is, do I? No clue. Here's my conversion. What's big F double prime? F prime. Now F prime, I can't take the derivative of a graph.
Slope.
I can take the slope of a graph though, can't I? Because isn't that what derivative is? All right? So, if I'm interested in big F double prime, that's F prime, little f prime, where does my slope change direction? When does the slope of little f change?
1, 2.
Yeah, its points of interest. Its sort of points of interest are going to be 1, 2, Well,
Not change it 3.
no, it doesn't change. It got to change from positive to negative. It changes, but it doesn't change signs.
So 4.
So 4, and then 6. Okay, and then what's that? 7. Okay. All right. The slope of f, is it positive or negative here? It's positive, so we get a happy face. The slope here is 0. That's kind of, I'll talk about that later. It's not happy or sad, it's just flat. What's the slope from 2 to 4? Is it positive or negative?
Negative.
Negative. What's the slope from 4 to 6? That's positive. Slope from 6 to 7 is negative, and from 7 on is flat, so it's 0. But what we've got now is it's concave up, concave down, concave up, concave down. Now, let's answer some questions. Right? You'll have to look at the questions because I have my chart up here. Okay. So answering part C, where is it increasing? Well, easy. Here and here, right? Part D, where does it achieve a minimum and maximum value? Looks like you got a minimum value. Well, your candidate for a minimum value is going to be 5, but was it lower at 0 or lower at 5? Look at the first chart.
Hey, I have a question. So, is this one restart at 0 for the increasing, or is it negative infinity?
0, because the only interval they've only given us information from 0 to 8.
And then also on the other side when it's decreasing, is it 6.5 to infinity or 6.5 to?
It only goes to 8. Yeah. They've only given us information from 0 to 8. All right. So, are there any points of inflection? Look at the chart. This is where it's got to change signs, right? 1 is not a point of inflection. It didn't change signs. It's got to change from positive to negative or negative to positive. It didn't change.
2, 4, 6.
So 4 and 6. Did everybody see the only points of inflection are going to be 4 and 6? Because those are the only place that it actually changed signs. Does this make any sense? Right? Now, the last little bit, and I'm going to need your help because I had to erase my chart. Everybody look at your big F chart, that first chart we filled out. We're going to plot points. So if we plot points, I remember at 0 we were at 0. What was big F of 1?
2.
Big F of 1 was 2. What was big F of 2?
5.
What?
5.
5. What was big F of 3?
6.5.
What was big F of 4?
4.5.
Okay. What was the next one?
0.
Hey, I don't know.
Yeah.
The first chart.
Oh, wait, sorry. 5
Oh.
is 2.5.
5 was 2.5?
Yeah.
Okay. What was 6?
3.
Okay. What was 6.5? 3 1/4 went up a little bit. What was 7?
3.
Okay. And then what was 8?
2.
Okay. Now, let's see if I can draw this. It says it's increasing up to 3. Look good. It looks like it's decreasing down to 5. Then it increases up to 6, right? And then I have to draw this. Oh Lord, how do I draw this? From 0 to 1, it's concave up. I can do that. 0 concavity means it's flat. then it's concave down to 4, then it switches to concave up to 5. Oh, no, concave up to 6. Then it's concave down to 7. And after 7, it's flat. You see how we created our picture? All right. Did this make any sense? All right. This is huge. Okay. So here's what I want everyone to do. And I'm going to